Hey, thanks for attending my talk. I intend to speak a little bit about Dask in the tabular data processing space, and then how Dask can work in an ETL concept and where its strengths are, so where it's especially well suited. This is the main topic. We will spend the first half of the talk talking about a bunch of improvements that Dask had over the last 1.5 years that make it more competitive in the large-scale data processing space, before we then move on to a ETL concept and what Dask can do there for you. So yeah, Dask data frame historically was like pandas, but in big. If pandas ran out of memory or it was too slow, then Dask was a good alternative, but it also wasn't very fast compared to other tools in that space. But this all has changed over the last 18 months. And then we look at an exemplary ETL style thing and look at a live demo to see how Dask can process just a shit ton of data in relatively short time. In March this year, we released a new Dask data frame implementation. The API is 99% exactly the same as the old API, but the underlying layers that construct how your query is executed completely changed. And I am a bit biased, to be honest, but have gotten a lot better and especially faster and more scalable as well. The main topics I want to hit today is how Dask improved the shuffling algorithm, how we chose a better string representation that especially helps in a distributed setting, and just how Dask now optimizes queries for its users. We will start with PyArrow-backed strings. Historically, pandas, and thus by extension Dask as well, used NumPy object data type to represent strings and everything else, which was often very memory intensive. Memory just blew up in distributed workloads, and also it constantly clogged the GIL, which is in distributed frameworks not very helpful. Dask, I think that was already over a year ago now, switched the default string representation to PyArrow-backed string data types. This fits nicely into the next talk, into the Apache Arrow ecosystem. And for us, this was mostly about performance. If you operate a lot on strings in a distributed setting with Dask, it's now roughly 2 to 3 times as fast, which is nice. But our users oftentimes care more about scalability and reliability over performance. So being a little slower is fine as long as you complete reliably. This is where PyArrow strings helped us even more. You can see on the right side the plot here. Memory usage just went down by over 50%, simply from switching object data type with PyArrow-backed strings. One caveat here is this was done on a data set with 20 columns, and only I think 3 or 4 of them were actually strings. So replacing these 3 columns with a more efficient layout already reduced memory by over 50%. If you have even more string columns, then the difference will be even more drastic compared to what we are seeing here. So basically, in the end, what we could do with these strings then was we just reduced the number of resources that we used to compute stuff by 50%, and we were still faster than the original implementation, which translates into a nice cost savings and a better performance just overall. This was the most, I don't want to call it trivial, but it was the easiest change of the 3 that I want to hit today. A way more complicated topic was how we improved the join performance. Joining on a single node is relatively easy because all your data is there, so you can just squash them together and see which rows match with the rows on the other side. In a distributed setting, you might have matching rows on one machine, and the matching row on the other side, on the right side, is on a completely different machine. So you have to make sure that the data are co-located on the same resources before you can do the actual merge operation that joins both data frames together. Historically, Dask used an algorithm that was not very efficient, to put it nicely. It loaded all of your data sets into memory, so you couldn't really process out of core, in the sense that you always had to have more memory available than your data set. And it also like overloaded the complete system. So the number of tasks with the old algorithm was log n times n, which as your data set grows, like basically blows everything out of proportion. And this was a complete rewrite. Like the algorithm that does these joins and everything else that requires worker-to-worker communication is completely new, and we basically enabled a method that allows us to scale linearly with your data set, with your growing data set. So you can basically scale arbitrarily now, if Dask generally works at that scale. Shuffling is not a bottleneck anymore. On a very high level, I won't go into too much detail here. Like we could talk about this for like 90 minutes and still wouldn't have covered everything that we did here. The historic task-based algorithm used an intermediate layer that created one task that had to be executed per input times output partition combination. And then there was a little bit of, or a lot of math involved, that instead of like getting an n square scalability, reduced this to log n times n, but in the end, like it was still like nonlinear growth. The new algorithm does, from a like user point of view, exactly the same thing. But this intermediate layer that was previously the problem was now reduced to a single task, which we call the barrier, which is just like the intermediate step between input and output of the shuffling operations. We are still doing exactly the same operations, but we are now hiding all this complexity away from the system. We basically replaced like high overhead tasks with like very, very low overhead alternatives that the system doesn't even notice at all. It's also offloading the data to disk, which means like when you shuffle all your input data sets, we write stuff to disk before we extract the outputs. This means that you can basically process out of core as much as you want. And we've run benchmarks where we process like tens of terabytes with like 500 gigabytes of RAM. You need enough disk available, obviously, because you have to write the 10 terabytes somewhere, but generally things work fine now. This is the point that I was hitting right now. Is like we are shuffling data at constant memory. So all the like growing data that we had previously is now offloaded to disk. So the system doesn't notice this anymore. These were the first two improvements. Both of them went live like last year. And then the biggest effort was that we added query optimization to Dask data frames, which means that Dask is now doing like SQL-style reordering of queries to just make sure that it executes stuff as efficiently as possible, and more importantly, doesn't do more work than what's absolutely necessary. Column projection and predicate pushdown is something, if you have a data set with like hundreds of columns and like billions or trillions of rows, but you only need like 3 of them, then Dask will figure this out automatically and drop everything else before you even read from storage. Like, as in the case that you have like file formats that support like column selection, like Parquet, for example. Historically, Dask was just reading everything and only dropping the columns that you don't need when you actually asked for it, which could be very, very much very late in the workload. So what we have here is like we have like 2 operations that read from Parquet, then we do a merge, and then we in the end select the customer key and the total of our orders. So our orders and customer data sets obviously have way more columns, but we only need those 2 plus order date. So what Dask historically did, it read everything at the top, then went into the join, transferred everything over the network, before it applied the filter, and then came the group by aggregation that actually reduced to those 2 columns. Now the new algorithm figures out automatically that the group by aggregation actually only needs those 2 columns, like customer key and order total, and then pushes this selection all the way to the top. So you don't even have to load data from S3 or Google Cloud Storage or Azure Blob Storage or whatever, wherever your data sources are located. It just now reads like maybe 10%, maybe 5%, maybe 20% of the data instead of everything, and also doesn't put everything into memory. Like in practice, like the filter is also happening directly in the read Parquet step, but that would have made this like plot a lot more complicated to understand. That's why this is a separate node. But in practice, this also lives up here. This was like one of the standard things that every like SQLite query optimizer does. Spark, for example, or just a SQL database. The other things we did was a little bit more tailored towards what Dask is good at or what it's not good at. Dask is very bad at like processing tiny partitions. Like normally you should have partitions that are like 200 to 300 megabytes. But this can, depending on what you're doing, you can end up with partitions that are kilobytes in size. And then Dask will just have a lot of overhead and not process your query very efficiently. So the query optimizer looks at the dataset size that you load into memory and also like in certain steps in between in the workflow and tries to hit these like 200 to 300 megabytes automatically. So we have a step in there that squashes your input files together so that we can create bigger in-memory representations of every partition. The funny thing about this is like this was, I think, a 3-line code change and made our benchmarks like 3x faster. So I would like a few more of those, but haven't found them so far. The way this happens is we basically look at what each column is in memory, and then based on the columns that we select, we try to respect the initial partition size. So if your initial Parquet file is like 300 megabytes, then we also hit this in memory. The probably like biggest complaint that Dask got historically from its users was that every merge was just shifting everything over the network all the time, which is oftentimes necessary, but in a lot of cases it's actually not. So if you look at this query, we have 3 read Parquet things in the top, and then we go down here. We merge on column part key, and then we merge again on column part key. Historically, Dask would have done something stupid in the sense that it does a shuffle join, which means that it sends everything over the network twice. So we need 4 shuffles, like 1 for left and right each time. The optimizer now looks at this and figures out that actually, like I've already shuffled the left side on the same column that I would shuffle again. So it basically does a no up here. And it checks a dedicated shuffle for the right side. And then we can perform a trivial join. Like our benchmark set had queries where you had 5 or 6 joins after another that always went to the same column. And these like got like 60, 70% faster because we just had a lot less writing to disk, a lot less network transfer, all the things that you normally don't want in an efficient distributed workload. This is something that's not general purpose. Like this only works if you have the same join over and over again over the same columns. Otherwise, it won't have much effect. But it's still like a nice improvement to make Dask more scalable. For users, like this change was obviously noticeable. If you rewrite everything, then you will introduce bugs eventually. But generally, it's a lot easier to use now because all the manual optimizations you had to do beforehand are now like automatically there, and it also scales a lot better. Like when we ran benchmarks, we had trouble processing 1 terabyte of data without putting a lot of resources onto it, and now this just like Dask just churns through the data. Over these 3 improvements, in the end, got us like a 19x improvement on some like trivial queries that didn't do any manual optimizations. So we went down from 950 seconds to 50 seconds, which might be hard to believe. I give you that, but that's why we are looking at live demo now. And what we are doing here is like we are executing a query that like reads from Parquet, then does a few filters before it merges and does a group by. This one is the old implementation where I disabled the new the query planning layer, the new optimizer, and also switched back to the old tasks-based shuffling algorithm. What you can see here, I already started the query, but nothing is really happening. This should show up now in a little bit over here. It just took Dask a long time to actually get anything running. So now we move this over here. So now we actually are doing something. And this over here uses the new implementation. Same query, I didn't change anything. And now we will kick that one off with like a 30-second delay or something like that. What we can see first is like it goes a lot faster to actually start. Another thing that's important is like we only have like 6,000 tasks. The number of tasks generally means like how much work the scheduler has to do. The old version had like close to 400,000 tasks, so it's like roughly a 60x improvement, which helps like the system, just the general system, but we still have to do the work. What we can see here is like we already churned through a bunch of our actual computations, while the one on the left is still like pretty busy with initial data loading. This is the data loading task here. And we still haven't read all the data. This is a little unfortunate. I think I am using a spot cluster in the background, and I think I just lost a bunch of workers, which means that we have to start over. That's not what you want for a demo. One of the things that is especially like interesting, I mentioned earlier that we are now shuffling data with constant memory. And we can see here that the cluster on the right side is pretty chill. It doesn't have a big memory usage. And the one on the left just keeps building up. If we would, like this runs a couple minutes on the left side, while the right side is pretty fast. If we would wait all until the end, then we would see that Dask runs heavily into spilling and has to offload stuff to disk to actually even get to the end. Like summarizing, we ran the left query basically twice, and we are done, while the left query is still pretty busy. If I would wait now, this would run for another 5 minutes, basically, until everything ran through. This is just to illustrate, you can now write pretty dumb queries, and it will just complete. Not a problem at all. While the old one had a lot of trouble with stuff that wasn't heavily optimized by the user. Dask now should do all of this automatically. So let me briefly stop that, and then we can go back to the slides. The second part of this talk is like, goes a little bit more into the ETL pipeline direction. Before we start with how Dask fits into that space, like this is a very crowded space where you have lots of tools available that you could use. What we understand generally under ETL is like that you extract data from somewhere. Oftentimes these are messy sources, like some unstructured format over here or some like XML or JSON over there. And then you do some transformation, data cleaning, just split data up to have a better format, like whatever fits your data model in the background better. And then you load stuff into a data warehouse-like system. This could be like a SQL database, but then it's probably not something where Dask is very good at, or something more suited for large scale like Snowflake or Delta Lakes or Google BigQuery, any of these systems. We want to focus more on the large-scale part because there are lots of tools out there that fit the single node case very well. So as I said, lots of tools. The question is, why is Dask like good at this? Dask makes it relatively easy to run stuff at large scale now with the query optimizer and the new rewrites and the joining algorithms. So there's not much work required to actually fine-tune anything. You can just write your code as is and then submit it to the cluster and things will run well. The even like bigger important thing that we will also see a little later is that Dask is Python only, not like Spark, which transpiles to Java. So you can define as many UDFs as you want, and Dask will handle all of those fine. Dask generally works well with like common big data like formats. We have connectors that are tailored towards like Snowflake, Delta Lake, BigQuery. These come all out of the box, and you can just install an extension of Dask, and then you're good to go, basically. So this makes it very easy to connect to arbitrary data sources. This is the point I want to make here. And then there is the second part, the messy data sources, like BigQuery, Snowflake, and like Delta Lake all have nice APIs. They follow a SQL-like pattern, so you can connect to those easily. But then you have stuff like maybe a REST API somewhere, HTTP requests or whatever. Or what we've actually seen a lot with our users and also our customers at Coiled is that people want to process all kinds of like real-world sensor data, which could be a sensor that is connected to the cloud, or it could be a machine that is somewhere out in the wild and just outputs data in an unstructured format. As long as you can read these data sets with Python, Dask will fit that space very well because it can just process any UDF. The only thing you have to do is like convert these unstructured or messy data sources to pandas data frame. And then there's also the part like Dask is Python only. It connects very well with all the like tools that exist in the PyData stack, or generally workflow scheduling tools like Prefect, Dexter, Airflow, whatever. Everything that has a Python API can generally trigger Dask jobs very well. One general example of how this could look like we run all our benchmarks with Coil because it gives us the easiest way of getting a cluster. You just like have a function somewhere that spins up a Dask cluster, then extracts the data from the source in some way. Could be a UDF, could be one of the built-in methods that Dask exposes. Generally, what we see when users connect to messy data sources is that they write a UDF and then just have like thousands or millions of files that they want to iterate over. And this is basically one line of code with Dask. And then like you do some stuff with your data to bring them into a format that you actually want before you then write the data to some output format that is better suited for downstream processing. This can either be with one of the like first-party integrations of Dask, like Delta Table or BigQuery or whatever, or you write, again, your own UDF that writes to the data target of your choice. So this is basically everything, again, that exposes a Python connector. Circling back a tiny little bit to the like integrations with Prefect, Dexter, and all the workflow schedulers, because you don't want to like start your ETL pipeline by hand. Running Dask with Prefect or Dexter is basically the same thing. Same as Airflow, is as easy as squashing a decorator onto your function. Like the deployment, including like all the data processing, everything is plain Python. So as long as like this tool can run Python code, you'll be good. We build a bunch of examples for our users to like, for them to have templates, and it's indeed like, it's like we're slapping a decorator on it, and this thing would run once an hour, once a month, once a day, whatever you need. Seeing this a little bit in a real world like thing. I have my cluster up and running here. This was the first step. It gives me access to like, I think 250 workers on AWS. It's quite beefy, but we had a lot of JSON files to process. Our data source is like basically one S3 bucket that has just like a couple thousand JSON files in it that give us access to a blown up table. Dask just exposes the read JSON functionality, and then you get your data into a nicely formatted data frame that you can then use to like do some transformations on it before you write it to a target source. We'll zoom in a little bit. What we do here is like this table has all kinds of information, and we only care about the customer part here. So we just extract the columns that are required for our customer table, which is like the key and the nation that the customer is based in. And then like we have a subset of this. And now it's the interesting part. Like you would probably do in a real world use case a bunch more transformations before you actually write to storage. Dask offers a map partitions, which basically applies the same UDF to every partition in the data frame. What I'm doing here is like my write function just writes to a Delta Lake. It takes the data frame, it's a pandas data frame that comes in, converts it to an arrow table, and then calls the write Delta Lake functionality from the Delta Lake package. What we'll now see here is like it's as easy as like a couple of lines of Python code, which lets us like transform JSON data into a Delta Lake without having to deal with any deployment. And we're basically done. Yes. This should just illustrate how easy it can be if you have a messy data source where the framework of your choice doesn't directly expose a connector that you would like. Dask all makes this very, very natural to work with. And so that's it. Thank you very much.
Thank you, Patrick. So is there any questions in the audience? Yes, I see one.
Hi. Thank you for the wonderful presentation. So the question which I had is, like you mentioned that for us to use Dask, everything needs to be converted into a pandas data frame first. So, I mean, there is a limitation of pandas that it can execute only on a single node. So in this aspect, how does it compete with likes of Spark or PySpark?
That's a very good question. That's something I should have mentioned a little earlier, probably. A Dask data frame consists of many, many, many pandas data frames. So if you have like 1 million of files, then your Dask data frame will probably end up being 1 million of pandas data frames. And then what Dask does, it orchestrates the computations on these pandas data frames. So all of them run in parallel and are distributed across your cluster. So like your Dask data frame is not like one big pandas data frame, it's just many, many small pandas data frames. And they can all run in parallel on as many nodes as you want.
And just another follow-up to that, like if I have to choose whether should I go for a Spark or a Dask for my ETL job, so what are the use cases where Dask is a better fit?
If you're integrated into like the Python ecosystem, then Dask just has better connectors to all of these things. We also think that our deployment is a little bit easier because Dask is like only Python. It can be pip installed and doesn't bring any heavy dependencies with it. While for Spark, you always need the Java dependencies also present on your machine. And speed is comparable now after all our like optimizations. So it's basically something where you are optimizing for UX and developer speed. And also how many UDFs, how many weird Python transformations you have. It just offers a little bit more flexibility in that space.
Okay, any more questions?
Thank you so much. Awesome presentation. You mentioned, tight integration with BigQuery, and I'm just curious, how is reading from BigQuery to a Dask data frame, how performant?
Good question. If you want to like read a big data set from BigQuery, we apply a chunking and then read from BigQuery in parallel. And for this, we use the integration that the BigQuery people provide to the Arrow interface. We basically use Arrow to extract the data from BigQuery and then convert it into a pandas data frame. It's just an embarrassingly parallel read from BigQuery, basically.
Another one.
Hello. What can you tell us about out-of-core analysis of the big data sets, and how best practice you have to partition the data to speed up the analysis? Thank you.
That's a very good question. Like, this was always a huge pain point with Dask in the past because it wasn't doing much in the sense of helping you choosing the good partitions. This should now be a lot better. Like, generally, I would recommend to optimize for like 300 to 400 megabyte partitions. And then Dask should normally keep those relatively stable over the lifetime of your workload. So ideally, you don't have to do much there. And generally, out of core, Dask will run embarrassingly parallel as long as you let it. And all the APIs that require a lot of cross-worker communication, like joins, shuffling, sorting, they all offload to the disk. So you can basically process unlimited out-of-core data. If you have enough disk available. That's one of the caveats.
Okay, so that's the end of the sessions. So we can still thanks Patrick.